So today we are going to start talking about two-dimensional kinematics. So remember, a dimension is like a direction. So up until now, we've actually been doing just one-dimensional kinematics, which is motion back and forth along a straight line. So today we're going to start talking about motion that happens in two dimensions. This would be motion in a plane. And to do that, we really have to first kind of improve and enhance our understanding of vectors. So we know vectors are quantities that have both magnitude and direction, and up until now we've used just a positive or negative sign to indicate the direction of a vector, because a vector can in one-dimensional kinematics, a vector can only be either in one direction or another, right? To the right or to the left, for example, and we use positive and negative signs to denote that. But in a plane, vectors can be pointing in, many more directions, so we're going to have to sort of improve our understanding. So let's just take a quick look at this question, right? A plane has an airspeed, that's how fast it flies, like relative to the air, of 200 meters per second, and is flying with an orientation of 30 degrees north of east. So this is like the bearing that it's going. So it's not going north, it's not going east, it's going like kind of northeast. The wind blows with the speed of 40 meters per second west. And it's asking how fast the plane is going relative to the ground. It's asking what angle the plane travels at relative to the ground, and then what is the plane's displacement in the north direction in 1 minute. So this is the kind of question that we should be able to do by the end of the day today, right? So I'm not going to do it now. I just kind of want to give you an idea of the sort of thing that we're going to be working on. Okay, so first, remember that a vector has magnitude and direction. And now that we're building a more sophisticated description of vectors, we're going to represent vectors often by arrows. So in the case of, in the case of this vector here, its length represents its magnitude, and the direction the arrow is pointing is its direction. But remember, this arrow is just a representation, right? So for example, we can use vectors, we can use arrows to represent velocity vectors, but velocity is not actually an arrow, right? And in the case of a velocity vector, the length would represent like the speed or how fast it's moving. So one property of vectors is we can move them around, and no matter where we move it, that doesn't actually change the vector because it has the same magnitude and it has the same direction, right? So we can take the same vector, we can slide it around, and the important properties don't change. Right, so these are all the same vector. I called it vector v. Notice I'm putting a little arrow over it to denote that it's a vector. Okay, we can add vectors. So if we want to add vectors, if we want to do this graphically, right, by graphically I mean sort of visually, we can use something called the tip-to-tail method. So if we want to do u plus v, all we do is we take vector u, and then we take vector v, and we put the tail of vector v at the tip of vector u, right? That's why we call it the tip-to-tail method. And the resultant vector would look like that, right? So the resultant vector is the sum of u and v. Right, so we took u, and then we put the tail of v at the tip of u to add those two together. Now notice that we could actually add them in the opposite order, right? So if we start with v, and then we take the tail of u and put it at the tip of v, it looks something like that. And if we look at the resultant, right, going from the tail of the first vector to the tip of the second vector, it looks like that. And these two resultant vectors are actually the same, right? So u plus v is the same as v plus u, which kind of makes sense because we expect addition to follow this property of, it's called the commutative property, right? You switch them around and then you get the same result even if you switch the order of the variables. All right, so this is called the tip-to-tail method. It's a way for adding vectors. All right, so what if we have three vectors? What if we want to do u plus v plus another vector w? Well, we just add them all tip to tail. So let's start with u, and then let's take the tail of v and put it at the tip of u, and then let's take the tail of w and put it at the tip of v. And then the resultant vector would point from here to there. Right? It looks just like that. Now similarly, right, we can add these in any order, and we should actually get the same resultant vector if we sum them. So let's start with w this time, and then take u. So we're going to do w plus u plus v. And if we go from the tail of the first vector to the tip of the last vector, We get something that looks like that. These two vectors, right, the resultant vectors, should actually have the same magnitude, so the same length, as well as the same direction. Right, so these are identical vectors, the resultant vectors. Okay, we can also multiply vectors. We can't multiply vectors by each other. It turns out that in order to multiply vectors by each other, it's a little bit complicated, and we're not going to get into that for quite a while. But it's very easy to multiply a vector by a scalar. So let's say we have vector u. Well, if we want to do 2 times u, basically u just gets twice as long. Right? So the magnitude just changes by the amount that you multiply it by. If we wanted to do 1/2 times u, it would look like that. Right? So the magnitude of that vector is halved. If we want to do -1 times u, well, you might be able to guess what's going to happen. That would actually change the direction. Right? So multiplying a vector by a negative actually changes the direction of that vector. It flips around, points the opposite way. So that would be -u. -2 times u would look like that. -1/2 times u would look something like that. Okay, now let's say we want to subtract some vectors. So vector subtraction, basically the way we're going to do it is if we want to subtract a vector from another, we're really just adding two vectors, but we're adding the negative of the second vector. So here's what I mean. Let's say we've got u and v, and we want to do u minus v. Well, all we need to do is we need to do -1 times v, and now we're doing just u plus -v. So we take u and we add it to this -v, right? So we're using the tip to tail method here, right? We're adding u to this -v, and then the resultant vector is just that. So that would be u minus v, right? The same thing as u plus -1 times v. Okay. Vectors also have algebraic representations. So for example here we have this vector a, and if we want to represent it algebraically, we can represent it in something called component form. So let's imagine x and y axes kind of set up like this. Now to write a vector in component form, we use the x component, which is basically how far it points in the x direction, and the y component, which is how far it points in the y direction. So vector a would look something like that. Right, because it's 1, 2, 3, 4, 5, 6 units of whatever. We don't know what kind of vector this is, so we don't know what it's measured in. But there's 1, 2, 3, 4, 5, 6 in the x direction, and 1 in the y direction. So we could write that vector as 6, 1. And really, these should have little vector signs over them, right? I think I'm just going to use bold instead of the vector signs because the vector signs got really hard to put into the PowerPoint. So just if it's bold, that means vector. Okay, so now for b, right, the x component of b is actually -2, and the y component is +3. So we could write this vector like that. Now, we could add and subtract these vectors graphically, but we can also do it algebraically. So let's say we want to do a plus b. Right? Graphically, we just add them tip to tail like this, right? Take a and then put the tail of b at the tip of a. We got a plus b right there. But if we want to do this algebraically, we can actually do this just by adding the components. So if I want to get a plus b, I can add 6 to -2, and that gives me the x component. And I can add 1 to 3, and that gives me the y component. Right? Basically, we're just doing this. Right? We add the x components, and then we add the y components. So in this case, it would look something like this. 6 plus -2, 1 plus 3, and we get 4, 4. And if you look at this resultant vector here, it is indeed 1, 2, 3, 4, 1, 2, 3, 4. Right? That is a vector with x component of 4 and y component of 4. So that's what it looks like if you're adding vectors algebraically. Right? Graphically, it gives you this tip to tail sort of visual. Algebraically, you're just adding the components. Okay, let's try another one. Let's say we want to do vector a minus 2 times b. So if we want to do it graphically, right, first thing we have to take b, but let's go ahead and do -2b, so that all we need to do is add a plus -2b. If we do this tip to tail, we take a put negative 2b there, write the tail of the second vector at the tip of the first. That would be the resultant vector, right? A minus 2b. Now let's do it algebraically, right? So a is 6 comma 1. Here we've got negative 2 times this is b right here, negative 2 comma 3. First thing, I'm going to distribute that. Oh, okay, that's just the same thing again. But first thing, I'm going to distribute the negative 2 through here, right? We're basically scaling the vector, so each of these is going to get twice as big, and the directions are going to change, right? That negative sign comes through. So negative 2 times negative 2 gives me 4, and negative 2 times 3 gives me negative 6. And now to add these, we add the x components, and then we add the y components. So 6 plus 4 is giving me 10, and for the y components, 1 plus negative 6 gives me negative 5. And if we look at this vector, if we count it, it should be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 units in the x direction, and in the y direction, 1, 2, 3, 4, 5, right? It's negative because it's down, right? I was calling up the positive y direction. Okay, so that's how you can add vectors algebraically as well as graphically. All right, we can also talk about a vector's magnitude in relation to its components. So remember earlier I said that a vector's magnitude is basically represented by how long it is. Right, so here's vector A. It's 6 comma 1. Those are its components. Now if we want to find its magnitude, we basically just want to find its length. Well, hopefully you remember from math that this is basically a right triangle, right? This is 6 and 1. So we should be able to use the Pythagorean theorem in order to find the vector's magnitude, right? We're taking the x component squared, right? 1, 2, 3, 4, 5, 6, plus the y component squared. That equals the magnitude of the vector squared. So if we square root that, right, that gets us the length of that vector. Right? The x component squared plus the y component squared is equal to this side squared. And then we're just taking the square root because we want to find the length of that side to get the magnitude. So in the case of this vector, we would just do that, right? 6 squared plus 1 squared. And then we take the square root, and that gets us that hypotenuse, which is the magnitude of the vector. It comes out to be about that, 6.1. Cool. Notice that we can also find angles if we need to by using the vector's components. So let's say this is vector v. It's got an x component and it's got a y component. Now let's say we wanted to find theta, or we wanted to relate theta to some of these other variables. Remember, you can always go back to SOHCAHTOA, right? Sine of theta is opposite over hypotenuse. Cosine of theta is adjacent over hypotenuse. And TOA, right? Tangent of theta is opposite over adjacent. But typically we're going to be wanting to relate the components to the magnitude, right? That's usually what we're going to want to do. So, right, if we use SOHCAHTOA, we can relate the x component to the magnitude using this, right? This v here, this represents the length of the vector, right? That's the magnitude. That's what this sort of double line sign here represents, right? So this comes from SOHCAHTOA. This is the ka part, right? Cosine theta is equal to adjacent over hypotenuse. If you rearrange, you get this, right? And then for this one, we could write it like this. And this is again from SOHCAHTOA, right? Sine theta equals opposite over hypotenuse. Opposite over hypotenuse, if you rearrange that, you get this. Okay. So I hope that was helpful. It might have been a lot. You might have to go back and look at some stuff maybe a couple more times. We're not going to be actually using this kind of notation that often. Mostly we're going to be adding vectors, but we're not going to be doing that much like sort of scalar multiplication and things like that. So let's look at this question one more time. They give us the speed of the plane relative to the wind. They tell us the direction it's flying in. The wind blows 40 meters per second to the west. Now it's asking us how fast the plane is moving relative to the ground. So the plane is flying in the air, but the air is also moving, right? That's what wind is. So that actually changes how the plane moves in relation to the ground. And if we really want to think about what's going on here, we have to use velocity vectors. So, right, this is sort of the motion of the plane by itself, right? This is in the air if there's no wind, right? That 30 degrees north of east, that just means, right, if this is the east direction, right, it's 30 degrees towards the northern direction from the eastern direction. So that's all this means here. Now, we also have the motion of the wind making the plane move an additional 40 meters per second to the west. So that means that, oh yeah, west is that way, to the left actually. So that's going to actually slow down the plane. So what this means is the total velocity of the plane is actually going to look something like that. Right? We might want to call that like the net velocity or something like that. Right? So this is the plane's velocity, but the wind is also blowing that way. So if you take the vector sum, that gets you what the actual velocity of the plane is. And that's what we're trying to find here in part A. So I think what I'm going to do now is I'm going to switch over to my iPad, which means I'm going to end this video. So now it's time to go ahead and move over to the next video and see the solution to this question.